So the next speaker is Jae-Seung Yeom from Virginia Tech. This is a relatively new collaboration compared to the older ones, and this is on epidemic simulations on large machines.
So today I'm going to talk about epidemics, contagion simulation software that we implemented in Charm++. And this is a joint collaboration between PPL, Lawrence Livermore, and Virginia Tech. So I'm going to go over the epidemics briefly and talk about what kind of scalability challenge that we have faced when we try to run this code on large-scale platforms and how we overcame them. And then finally, I'll present the performance results. So epidemics is an agent-based simulator. An agent represents a person in the social network, and the interaction between people are computed by the other types of objects called locations. And we represent social network as a bipartite graph like this. There are two different types of vertices, and the edge connects the vertices from different types. And a diffusion event may lead to interaction may lead to a diffusion event, and such as the disease infection. And an agent has its own state machine, independent state machine called PTTS, probabilistic time transition system. And in PTTS, a transition can happen spontaneously, such as recovering from disease after a random period of time. Also, it can happen by an external trigger, such as disease infection. So this is basically what epidemics do. And the key input of the epidemics includes a population data set. And for this study, we use a population data set, different size and geographic locations represented. And these data sets are generated based on sources available to public to match the demographic distribution of the real population of the United States. In epidemics, each iteration represents the day of the social network. So in a day, there are two computation phases followed by a reduction phase. So at the first computation phase, each person computes its health state and then also determine which locations to visit during the day. And then while doing so, it sends out visit messages to the locations to visit. And at the end of the phase, there's a global synchronization to make sure the delivery of all the messages. So this is necessary because there's no a priori information of the source or the number of messages to expect. And then in the second phase, locations compute interactions between visitors. And while doing so, it sends out, if there's an infection event, it sends out the infection notification message to the person who got infected. And then there's a global update of simulation scenario variable. So we distribute person data. So we have two different types of char arrays here, person manager char array and location manager char array. And we distribute person object across these char array elements and location object across these location manager elements. So that's how we use charm underneath. And there are features that we use from the charm. So we use either CD or QD for the synchronization, and we rely on TRAN for handling a large number of small messages. And we also take advantage of the SMP, and we also speed up the data loading using the latest interoperation for MPI-IO. And we use a projection to diagnose the performance problems. With epidemics, both the strong scalability and weak scalabilities are important. For example, a few years ago, when there was an avian flu pandemic going on, the health scientists and government policymakers required the simulation results for various scenarios every morning. So that's what motivated this. And then also, we currently have population data synthesized for the entire United States, and we plan to extend this to the global scale in the future. So we use large-scale platforms such as Blue Oryx and Vulkan, And that's when, so when we first started to run our code on these platforms, we noticed some unexpected scalability problems, and that's the main focus of this talk. So just to get a sense of how the code behaves. So in epidemics, we have large portions of data accesses and branching, and very small portion of floating point computation. So there are 58.3% of L1 cache, data cache accesses, and 19.3% of branching, and 70% of those branches are conditionals. And the yellow bar here shows the miss ratio of the conditional branch, and this green bar here shows the L2 data cache miss ratio. And we talked about the phase of computation in the algorithm. So this blue represents the portion of the time spent in person computation phase, and the orange represent that of the location computation phase. So when we first tried to run this code on large-scale platforms such as BlueWaters, the strong scaling behavior was not satisfactory, so it stopped scaling at 1K cores. So our first optimization effort focused on reducing data accesses and branching. As a result, we got significant improvement in weak scaling. The execution time was reduced by at least 40%, and the memory footprint was reduced by 50%. And the plot on the left side shows that in terms of the ratio of the hardware counter before and after optimization. So, for example, in this case, the L1 cache access ratio is less than 0.8. That means that it is reduced by at least 20%. But the strong scaling didn't really improve. It hasn't improved much. So we further took advantage of the SMP mode in Charm++, and that made us go a little further. But it was apparent that we were hitting another bottleneck. So that's what we are going to talk about. And those bottlenecks were actually from the data itself, not from the code or the runtime. So there was extreme variance in the load of work, originating from the held property of our data. And there is trade-off between data locality and load balance. So if you want to optimize one thing, then you may have to sacrifice the other thing. And epidemics also generates large amount of fine-grained messages. So for example, you can generate as large as 1.5 billion messages, less than 40 bytes each per iteration. And there's uneven amount of communication among processors. So to optimize the locality, in other words, to minimize non-local accesses in processing graph data, we rely on graph partitioners. And because graph partitioners allow us to specify application-specific load balancing constraints via the vertex weight in optimizing locality. So for that, we developed load estimation model like this based on function approximation approach. So the target of the model is the load, what we call load, and it's a relative processing time of location vertex. So and the input to the model is the application variable, such as number of events. So each visit to a location creates two events, an arrival event and a departure event. And edge from a person to a location represent a unique visitor, and a visitor may visit the same location multiple times. So we do this by using piecewise linear regression, and we observe the average error from 5 to 7% across the platforms that we tried. And we only use the statically available information to do this. And in the future, we would like to include the dynamically available information to handle dynamic load variation due to the scenario changes of the simulation. So when we applied this load model, the graph partitioner, um, the estimated speed up for each data set was like, it was bounded. So it didn't go beyond a certain point. So this estimated speed up is computed here as the total load divided by the maximum of total load per partition. So to get further insight on what's going on there, so we conducted an analysis based on some simplifying assumptions as this. So we assume the degree in the graph follows a power law distribution. For example, in other words, the number of vertices with the d edges are proportional. It's proportional to the exponential term of d with the negative exponent. And we assume that the complexity of work at the location vertex is order of degree. And then, so we further assume that the vertex load is the degree times some constant. So the goal here is to find out the maximum, the upper bound of the speed up. So we compute that by dividing the total load in the data set by the maximum load of a vertex. So we can do that by summing the load of all vertices, and then that we can compute by alpha times size of the data times the average degree. And the maximum load is with the maximum degree from the vertex load model. So by substituting these two terms here, you get the relation at the bottom. Now, to compute this log of Dmax, we have further assumption from the power law degree distribution that there is only one vertex with the maximum degree given the size of data D. From that, we can we get this relation and we substitute log of Dmax, and we finally get the upper bound scaled by the upper bound of the speed up scaled by the size of the data as this formula. So we know that the beta and C and D are all constant, but we don't know whether the average is constant or not. So we compute the D average as the expected value of the degree, and the degree ranges from 1 to the total number of vertex in the data minus 1. So the denominator here is from that from here. So the sum of the probability equals 1. So we get that from there. And this is just the probability of the power law degree distribution. So we know that this one converges. It's known as P-series, and it's known to converge when the beta is greater than 1, and which is the case here. But this one doesn't converge. It only converges when beta is greater than 2. The average is not exact constant. So what we can do here is that we can further proceed with numerical computation, and then this shows how the speed of upper bound scaled by the data size is bounded in terms of size of data and the power law exponent. So to pull this bound upward, we need to add some positive term here. And that's what our domain decomposition accomplishes. We do that by splitting heavily loaded location into sub-locations. And we choose to split heavily loaded location into sub-locations rather than just distribute location data at a final granularity, because that's better for the scalability, handling, and addressing the data, and also for efficiently sharing data within a location, such as zip code or coordinate. The plot on the top right side shows the estimate speed of upper bound scaled by the size of data for each state data of the United States. So we have 48 states in contiguous US, and DC, including DC, there are total 49 last year. And this is before the domain decomposition applied, and then after applying domain decomposition, we pull this dash upward. We pull this scalability bound upward. So we do this. We achieve this by only splitting 5% of the locations. And this shows how the degree distribution and load distribution and estimate speed up changes as a result of decomposition. The top row shows the one before decomposition, and the bottom row shows that those after decomposition. Before the decomposition, some vertices had load of almost about million, while some load has only one. So there's huge variance in the load. So in addition to the domain decomposition, we also use various data distribution strategies. So we have, the example that we have here is that we divide 4 locations between 2 processors. So each location has zip code, location ID, and the estimated load by the model. And to split these locations between the processors based on zip code, we first sort the location by the zip code. And then for the same zip code, we sort the location by the location ID. And then we divide these locations evenly in terms of the number of locations. That's one method that we try. And the other method that we try is that we evenly distribute these locations in terms of the sum of the cost. That we denote that case as ZC here. And the lines here on the upper graphs connects the locations in sequence. And the dots shows the amount of location load estimated by the model. The size of the dot it's proportional to the amount of load estimated. So this one is for Iowa, and this one is for Michigan, and certain region is not really loaded. And in fact, there are 2 different types of locations in our data set. At least that's how we categorize them. So one is home locations, the other is non-home locations. So, and we treat them separately, but in the same way. So we first divide non-home locations and then divide home locations. And then we assign people data to their home. So if you see it here, this shows actually the state boundary. But here, it's actually some locations are beyond the state boundary because we want to include all the locations that people visit within that state. So people visit locations within 15 miles radius from their home. And based on this distribution, the first processor will have L1, L2, L3, and H1 and H2. And second processor will have L4 and H3 and H4. And the people living in these homes. So I'm going to show some performance results here. So this one shows the impact of domain decomposition and data distribution strategies that we just talked about. So there are more data distribution strategies. So RR stands for round robin, which mimics the random data distribution. And GP stands for the distribution based on graph partitioning. And Z stands for the distribution only based on the zip code, and GC stands for the distribution based on zip code and cost. And the split log stands for the domain decomposition that we talked about. The biggest impact here is from the domain decomposition. So among those with domain decomposition, graph partitioning performs the best, and the zip code and cost-based distribution performs closely to the graph partitioning. But the distribution only based on zip code ignores load balancing and does not perform well, such as these yellow curves here. So there are 3 schemes that optimize locality in some way. So graph partitioning and zip code cost-based and zip code-based. And there are 2 schemes that balance load. G-code and code space and graph partitioning. So this one shows those decomposition and distribution impact on load distribution. So the y-axis here is a processor line, and the x-axis here timeline. So this shows what each processor is doing over time. So blue represent the person computation, orange represent the location computation, and red represent the receiver's message handling. So as you can see, with domain decomposition, there isn't much peak with location computation. But without it, there are huge peaks. And even with domain decomposition, if you don't optimize for locality, there are peaks like that. And with graph partitioning, the person-phase computation is shorter because there's less interference for receiving the messages, because some communications are local. And this result shows the impact of domain decomposition and data distribution on the communication in terms of the amount of data received per processor in megabytes. So those plots on the right side is with domain decomposition, and the one left side doesn't have domain decomposition applied. So again, there's a lower peak with domain decomposition. And there are two schemes that optimize for locality, graph partitioning, and G-code based, actually three schemes, G-code and code spacing as well. So with those cases, the total volume of communications is less compared to the other case. But with graph partitioning, there are huge peaks like this. It's because graph partitioning minimizes the total edge cut rather than balance the cuts across the partitions. So this shows the largest strong scaling result that we have so far. This one is from the blue waters. On the top right one is from the Vulkan, BlueGenQ. And the one at the bottom is from some InfiniBand cluster with Xeon processor. So with blue waters, we achieve a strong scaling up to 300, using 352K cores. I think I was using almost 99%, 6%, 99.6% of the total XE nodes over there. But I wasn't using the XK nodes. And with BlueGenQ, I ran it up to 128K cores because of the resource limitation, not because of the machine size. The machine size itself is 3 times larger. And as you can see, there's a big improvement from TRAM compared to the other case. But in this case, TRAM wasn't available at the time, so I don't have that data point. So the difference between red and the black shows the results of domain decomposition. And this is the weak scaling performance results. Here, we have the result from Blue Waters and Vulkan and InfiniBand cluster. And the difference between green and blue shows the results that shows the improvement from the domain decomposition. And the difference between red and blue, in this case, red and green, and again, here, red and blue, shows the result of low-level code optimization that I talked about earlier. In summary, we analyzed how the heavy-tailed property of the input graph limits the scalability of the application, and we introduced an application-specific workload model as well as the composition method, and we enabled data distribution with the application-specific information, and we finally demonstrate the strong scaling that is 5 times larger than the best known so far, although it may be not the fair comparison because the previous best scaling was based on XT5 platform, but ours are based on XT6. So that's the end of the talk.
For your, I guess, both sets of results, what was your configuration? Were you using threads and MPI? Or on top of Charm?
Yes,
within,
Charm++.
And so how many threads or MPI tests did you have, particularly on Blue Gene?
So on BlueGeneQ, actually on both platforms, I use 4 processes per compute node and 12 worker threads per compute node. Actually, 4
Per compute
worker
node.
threads per process.
Any other questions? Okay, let's thank Jae-Seung again.